All right, chapter 8. Chapter 8 is probably the most important chapter in this class because what chapter 8 really is it's the bridge between probability and statistics. This class is called statistics. But after the second day of class, we went to probability. So we kind of left statistics. I told you, like, what is the goal of a statistics problem? We talked about that first couple of days. And then we changed subjects to probability. So chapter 5, 6, 7, and 8 is all probability. But then after this chapter, we will go back to statistics. Starting next class, we'll be doing actual statistics problems. But everything that allows, the stuff that allows the statistics stuff to work is this probability stuff. So that's why we have to talk about all this stuff. So chapter 8 is really the bridge between probability and statistics. Now, let me say one more thing about chapter 8. In the past, I have told students that chapter 8 is the hardest chapter in the book, but I don't know if that's true now that I think about it more. It's going to be, basically, chapter 8 is going to go in like two parts. The first part is we have to conceptually understand what chapter 8 is about, like what's going on, what kind of problems are we trying to solve in chapter 8? Okay, so that'll take some time. But then after we understand that, the last part of the class, which is what your quiz will be on, okay, it'll be based on like the stuff we learned at the end today. It's really easy because all it is Z transformations. Okay, so in other words, I've told you this before. Section 7.2, that was the section where we learned about normal distributions and we did Z transformations and all that stuff. My opinion, that's really easy. If you don't agree with me, then study it enough so that it is very easy. But once you understand how to do Z transformations and finding areas under normal curves and all that stuff, once you understand that, then the end part of the stuff we're going to learn today is all that. All we're going to be doing, the conclusion of the stuff we're doing today is we have a normal distribution, and if you have a normal, anytime you have a normal distribution, you want to find a probability, you do a Z transformation. So the stuff we're doing today is identical, not exactly identical, but almost identical to stuff we did in section 7.2. That's the end stuff we're doing today. So it's all Z transformations. So again, if you're good at Z transformations, the end of what we're doing today is nothing new. But we have to understand the situation we're in today. And that's gonna, take some time. That's gonna be the first part of the lecture. So we're gonna do section 8.1 and 8.2 today, but I'm gonna spend almost the entire lecture on section 8.1. Section 8.2 is just a small extension of section 8.1. So we're going to spend everything except for the last 15 to 20 minutes on section 8.1. And once we completely get 8.1, then we'll do some 8.2 problems, and then that'll be the end of the story. All right, so let's see what it says. What does it say here? Section 8.1, the random variable x bar and its distribution. And section 8.2 is the random variable p hat and its distribution. So we've got two special random variables we're going to look at today. One of them is called x bar. The other one is called p hat. So I want to make sure we completely understand these random variables, but we're going to focus right now on the random variable x bar. Okay. Remember that every time I say random variable, you need to think that there's a bag with numbers in there, and we're going to draw, this is me trying to draw a hand, we're going to draw one number out of the bag. Every time I say random variable, we got a bag of numbers, we're going to draw one out of the bag. And but we have to understand, what is the story with this random variable x bar? What does it mean? We want to really dive into the story today. Okay, so that's the plan for most of the day. Then we'll do the p hat stuff later on. Okay, so the random variable x bar and its distribution. Okay, so I'm going to take you back to first day or maybe third day of class. All right, here we go. And again, guys, because I do feel like this is not the easiest section in the world, make sure you guys focus hard. And I'm going to remind you one more time of a lot of stuff I've told you throughout the semester so far, so that we have a good foundation of what's going on. So this is what I've told you. Okay. In every probability problem, you're about to do something. That something you're about to do is called the experiment. Okay. The experiment has outcomes or results. In other words, once you do the experiment, once you do the thing you're going to do, you end up with the result. Like when you flip a coin, it could either land on heads or tails. Heads is a result, tails is a result kind of thing. But anyway, you're about to do something. That thing you're going to do has results. And what we're going to do is we're going to focus on one outcome, one result, and say, what's the chance that that result happens? Okay, so that's every probability problem is like that. Okay, they're saying you're about to do something and it has results. The thing you're going to do once it's completed has a result. And we're going to focus on one of those results and say, what's the chance that that one result happens? And sometimes instead of focusing on just one result, look at this group of results and say, what's the chance that that group will happen? A quick one to keep in your mind is like rolling a die. So let's say the experiment is you're going to roll a die. So the outcomes are 1, 2, 3, 4, 5, 6. So I'm going to pick an outcome, like I might pick the number 5. I'm going to say, what's the chance of obtaining the number 5? And I'm sure you know the answer. I don't need the answer right now. But that's an example of a probability question. Or instead of picking the one outcome, okay, instead of just the number 5, I might look at a group of outcomes like the even numbers. So the 2, how am I going to circle this? Okay, fine, I'll just circle them all individually, 2, 4, 6. And I could say, okay, so the experiment is we're going to roll a die, and I'm going to look at the group of outcomes, the even numbers, and I could say, if I roll a die, what's the chance I get an even number? What's the chance I get one of these? Again, I don't need the answer. But every probability problem works like that. Let me say it all again. Every probability problem, we're about to do something. The thing we're going to do has results or outcomes. And we're going to look at either one outcome or a group of outcomes and say, what's the chance of that one outcome or that group of outcomes happening? That's every probability problem. Okay. Now we're going to look at a few examples. And again, I'm kind of taking you back to first day of class here, but okay. In every probability problem, you're about to do something. For example, the thing you could be doing is you're going to roll a die once. Okay. And again, when you roll a die once, you know what the outcomes are, the possible outcomes. Either you're going to get a 1, a 2, a 3, a 4, a 5, or a 6. So for example, I could focus on just the number 5 and say, what's the chance that we roll a 5? Or again, instead of just looking at one result, I could just look at the even numbers, which is a group of results, and saying, what's the chance if I roll a die, I get an even number? Again, I don't want an answer, but that's an example of a probability question. Here's a little more complicated one. We're going to randomly select a student in the class and ask for their age. So why is that a more complicated experiment? Because it takes 2 steps to do it. When you roll a die, it takes 1 step. You just roll the die. That's it. But for the second one, you got to first select the student, then you have to ask them for their age. So it's like a 2-step experiment. You have to do 2 things to get a result. Picture of the situation could look like that. So we randomly select the person and get the number 18. I ask them, hey, how old are you? They say 18. Then I can say, what's the probability I end up with the number 18 after I'm done with this? After I select the student and ask them for their age, what's the probability I get the number 18? Or I don't have to pick the one number 18. I could pick a group of numbers and say, what's the probability I get somebody in their teens? Okay, kind of thing. So that's not just 18, that's 19, 18, 17, 16, whatever, all the different teens, right? Okay, so that's a little bit more complicated experiment. Here's an even more complicated experiment. So in this one, it says we're going to randomly select 3 students in the class, ask each one of them for their age, and find the average of their ages. Why is this a more complicated experiment? Because it takes 3 steps to complete it. You have to first select 3 students, then you're going to ask each one for their age, and then you're going to calculate the average. It's 3 steps. In order to complete the experiment, you got to do 3 steps. Here's a picture of the situation. You select 3 people, ask each one of them for their age, and then calculate the average, meaning you add the numbers and divide by 3 since we have 3 numbers there. Okay. So a question can say, if you randomly select 3 people from the people in this class, ask each one for their age and find the average, what's the probability you get an average of 21.3? Or they can say, what's the probability, instead of just picking one possible answer like 21.3, what's the probability that the average you get is in the 20s? Okay. So these are the kind of questions we want to answer today. Actually, to tell you the truth, the type of question we're going to work on in section 8.1 is very close. It's actually pretty much exactly like the last example. Okay. But I want you to notice as we went from the first one to the third one, the experiment got a little bit more complicated. Okay. So how do we answer a question like that? If it says we're going to randomly select 3 people in the class, ask each one for their age, and find the average. What's the probability we get an average of 21.3 or an average in their 20s? How can we answer a question like that? Especially when it's a complicated experiment. Okay, remember, in every probability problem, you're going to do something. That something you're going to do could be simple, like this, or complicated, like this. But either way, we're going to do this experiment and ask, and then pick an outcome, a result, like 21.3, and say, what's the chance that that will happen? Now, how do we answer a question like that? How do we do it? Okay, so to find the answers, you need to make a bag with all the outcomes of the experiment in the bag. Okay, I've said this to you before. I know we've seen a million different kinds of experiments, but no matter what experiment we've looked at, every experiment is equivalent to drawing a number out of a bag. So here's what I'm telling you. You know the type of problems where the problem says, here's a bag, you're going to draw once out of the bag, find the probability of this. Okay, so we've got one bag, we're drawing one time, find the probability of this happening. Get good at those kind of problems. And then every problem, no matter how simple or complicated, can be treated just like that kind of problem. And this is telling us how to do that. To find the probability involving these experiments, you need to construct a bag containing all the outcomes of the experiment. Here's the first experiment, rolling a die. So if the problem says you're going to roll a die, what you do is you imagine a bag with all the results of rolling a die once. And here are the results. And now I want you to forget that the problem said you're going to roll a die once and pretend the problem said you're going to draw, again, this is me trying to draw a hand. You're going to draw one time out of this bag. It's the same question. If I say we're going to roll a die once, what's the probability it lands on 5? Or if I say you're going to draw one time out of this bag, what's the probability you select the number 5? That's the same question basically. Okay, so that's how you turn it into a drawing once out of a bag problem. The way you do it is put all the outcomes of the experiment in a bag. That's all you do. Figure out what all the outcomes are, put them all in a bag. Let's go take a look at the second one. It's a little more complicated. Here it says we're randomly going to select a student in this class and ask them for their age. Okay, so again, it's a little more complicated experiment, but if you wanted to answer probability questions, like if I say, if the problem says, you're going to randomly select a student from the class and ask for their age, what's the probability you get an 18-year-old? Or what's the probability you get somebody in their teens? Or what's the probability you get somebody in their 20s or something like this? If you want to answer this question, what you have to do is you have to make a bag, okay? And all the outcomes, all the results of doing this experiment have to be put in this bag. So I want you guys to help me out for a second, okay? So I want everyone in here, if you're willing, to type your age in the chat. If you're not willing, that's fine. You could we'll just skip you if you don't want people to know your age. But otherwise, if you don't mind, please type your age in the chat real quick. Okay, so everybody do that. We only have 7 students in here, so we're not going to get too many results. But let me see here. Okay, we got 3 so far, 24, 25, 21. Another 21. Okay, no one else is responding, so we'll just go with those 4. That's fine. Okay, so now, again, what you do is you look at the experiment. What are we doing? We're selecting a person and asking for their age. Here are all the results we can get for the people in this class. So now if I say I'm gonna randomly select someone in this class and ask them for their age, you can just think of it as instead, I'm gonna draw one time out of this bag and find whatever the probability is. I'm gonna randomly select a person from the people in this class and ask them for their age. What is the probability I select a 21-year-old? Let's say that's the question. Well, then you can just pretend that the problem says you're going to draw once out of this bag. What's the probability you select the number 21? So probability of getting the number 21. All right, someone tell me the answer real quick. What is it? Okay, someone in the chat is writing something. Let me see. 2 out of 4. Yeah. Because there's 4 numbers in the bag total. Numbers on the bottom is always how many things are in the sample space. And I want to know the probability of selecting a 21. There's 2 21s. So 2 out of 4. Yeah. So that's how you answer the question. And this is for every problem, no matter how simple or complicated it is. What you have to do is figure out what all the outcomes are and put them all in a bag. And then just pretend the problem says you're going to draw one side of the bag. And this is no matter how simple or complicated the experiment is. Let's go to a third one. Okay, so here we go. So this is the most complicated one, but again, this is the kind of problem that we're going to be working on today. Okay, it says we're going to randomly select 3 students in the class, ask each one of them for their age, and find the average. So it's a 3-step experiment. So experiment is more complicated. Okay, we're going to select 3 people. We're going to get the ages of each of those 3, and then we're going to find the average. We're going to add them up, divide by 3, and we're going to get a result. And I'm going to say, what's the probability you get 21.3 as your final results? What's the probability your average is 21.3? Or like I said, what's the probability your average is in the 20s or something like that? Okay, now how would you do a problem like this? Again, you got to make a bag, but it is more complicated. So let me just say that, okay, so the ages that we got of the people, so 4 people in here gave me their ages, right? Let me remember what they were. So there were 2 21s and a 24 and a 25. I'm just going to call them, I'm not going to use your actual name. So just a student A, student B, student C, and student D. So student A was 24 years old, student B is 25, student C and student D are 21. So if I say we're going to select 3 students from the class, ask each one for their age, and then find the average, well, I want to see what results we could get. So let's go ahead and select some students here. I'm going to select, let's say the students I selected were A, B, and D, for example. Student A, student B, student D. Then the ages I get are 24, 25, and 21. And then if you find the average, you have to add them up and divide by 3. Let me do that real quick. 24 plus 25 plus 21, 70 divided by 3. I'm getting 23.3. That would be a number that goes in the bag. That's one of the results of doing this. Now I'm going to do it again. I'm going to select 3. I'm going to select another group of 3 students. Let's say this time I use A, C, D. Those are the 3 students I select. Okay, so then the age for A is 24. The other 2 are 21. Okay, so I add those up, divide by 3, and I get 22. The average age of those 3 students is 22. So I put that in the bag. You got to keep going until you've done it for all possible groups of 3 students. If you switch the order around, it is a different group of students. So if I write B, D, A, it's the same 3 people as those, but think of it as I'm selecting one at a time. So this means I selected student B first, where here I selected student A first. So it is a different group of 3 students. Well, it's a different selection kind of 3 students. And if I write down the ages, this is 25, 21, and 24. And the average of those is also 23.3. So 23.3 is going to be in there again. Also, if we're drawing, they should tell you how we're drawing. We're going to be drawing with replacement. So if you draw with replacement, you could get, for example, the same student 3 times, A. So the average of those ages is 24. And in this way, you have to fill up the bag, okay? So the idea is, that's for every probability problem, no matter how simple or complicated it is. Make sure you understand the experiment, no matter how simple or complicated it is. Figure out what all the possible results of that experiment are, and you put them all in a bag. I'm not going to finish this bag right now because it would take some time. There would be, let me see, there would be 64 things in this bag if I was to finish it, which I won't finish it right now, but we'll do an example in a minute where we do make the entire bag. But then once you know the contents in the entire bag, then you can answer questions like, what's the probability I get, like I can say, okay, what's the probability that the number I get is 23.3? Well, let's say you knew that these were the only 2 times that you get 23.3, which is not true, but let's pretend it was. Then the top answer would be 2, because there's 2 23.3s. And the bottom would be, what did I say it was? 64? 2 out of 64. So you make a bag, put all the outcomes of your experiment in the bag, and then to answer the question, you just pretend that you're just going to draw one time out of the bag. When they write the question, or when I write it on a quiz or an exam, it's going to be in this complicated way. They're going to tell you this entire procedure you're doing. We're going to draw 3 students. We're going to randomly select 3 students from the class, ask each one for their age, and find the average. What's the probability this happens? And what you're going to do is you're going to make this bag with all the outcomes in it and pretend I said we're going to draw 1 time out of this bag. What's the probability that I end up with this? That's how every probability problem works. Let's move on. Okay, so there's just a couple little things here. So this is the type of variable we're going to study in this section. So we're going to look at one specific variable where we're doing basically this, okay? This is the type of variable, it's called x bar. We're going to call it x bar. Normally for random variables, we use the letter x. But we're calling it x bar. This special one that we're looking at today, we're calling it x bar. The reason is because x bar stands for sample average, okay? It means you're going to take some numbers out of a bag and find the average, and that's what we're doing. This is like a sample of 3 students, so we have their ages, and we're going to find a sample average. Okay, so for every problem in section 8.1, we're going to be using x bar instead of x. Okay, x bar is a sample average. Okay, let's move. So everything I told you so far was kind of like a recap, but it's kind of like the final time I'm going to tell you that, so I'm hoping that now that we've gone through everything up to chapter 7, that it's making some sense. I tie in everything, and I'm hoping that's what happened. Okay, so I'm going to tell you this idea a couple times. The x bar random variable. In every problem in section 8.1, it's going to go like this. They're going to start you out with a bag with numbers in it. Okay, so you start off with a bag of numbers, and we're going to call it x. Here's a picture of a bag of numbers. There's some bag with some numbers in there. The numbers could have a meaning or not. For right now, let's just not worry about the meaning. So we start off with a bag of numbers called x. Now, if you draw 1 time out of this bag, the answer you get is a value of x. The reason I care about that sentence there is what's going to happen in all these problems, there's going to really be 2 random variables going on. There's going to be x and there's going to be x bar. X has to do with the original bag and has to do with doing something once. So if the problem says you have a bag and you're going to draw 1 time out of the bag, then the question is about x. Okay, that's very important. But most of the time, they're not going to ask you that. But we are going to do one example where we ask that today. But be prepared. So if they say, here's a bag, we're going to draw once out of the bag. What's the probability this happens? Then the question is about x. And then you just look at this bag and you answer the question and nothing else to talk about. Okay, but we're not going to draw once out of the bag. In section 8.1, the experiment is very specific. Here's the experiment. It actually takes, I have to say 3 things, depending on the way you look at it. It's either a 2-step or a 3-step experiment. Okay, so here's what's going to happen in section 8.1. I'm going to say it in 3 steps. First, you're going to be given a bag of numbers. That's like the first step. And the problem is going to say, you're going to draw some numbers out of the bag. They'll tell you exactly how many. Like we're going to draw 10 numbers out of this bag, and then we're going to find the average. So that's like a 3-step. So it looks like 2 steps there, depending on the way you look at it. If you want to mention the bag or not, that's like a 3rd step. So let me say it again. Every problem in section 8.1 goes like this. We start you out with a bag of numbers. We're going to draw some numbers out of the bag, not 1. We're going to draw many numbers, like 10 numbers, 20 numbers, 80 numbers, whatever. We're going to draw a sample of numbers out of the bag, it's like a sample. And then we're going to calculate the average of the numbers that we took out of the bag. So if we draw 10 numbers, we're going to add them all up and divide by 10. When we're done, what's the probability this happens? What's the probability the average you get is, less than 10? What's the probability the average you get is 7.3 or something like this? That's the experiment in section 8.1. Let me say it one more time because it's very important. In section 8.1, the experiment, the procedure, the thing we're looking at, we start off with a bag of numbers. It's going to be called X, the bag that they start you out with. It's some bag with numbers. And here's what we're going to do. We're going to draw some numbers out of the bag. So we're going to take a sample, and we're going to calculate the average of all the numbers in the sample. The average of all the numbers in the sample is called X bar. That's what X bar stands for, sample average. So we're going to take a sample and calculate the average. A sample from this bag. Okay, and again, N, which is how many numbers we're drawing out of the bag, that'll be given to you. And then again, I want to answer probability questions. How do I answer probability questions? It's a complicated experiment. Okay. So what you do to answer probability questions, what you're going to do is you have to imagine you go through this procedure. You draw 10 numbers out of the bag, calculate the average, give me an answer you can get, then draw another 10 numbers, calculate the average of those, give me another number you can get. You keep doing this over and over until you've done it for all possible samples. And you put the answers in a new bag. So if I want to answer questions about this experiment, I have to build a bag for this experiment. So there's going to be two bags going on. There's going to be the bag in the question that they give you. There's going to be another bag that you're going to construct. You construct the second bag so you can answer the question. Okay, but the first one is just given to you. So that's what it says here. So you create a new bag called X bar. And here's what it is. And every single number in this bag was obtained by doing this to this bag. For example, imagine the problem said we're going to draw, let's say n was 3. So we're going to draw 3 times from this bag and calculate the average. If you took the numbers 7, 3, and 9 out of the bag, you find the average of 7, 3, and 9, 7 plus 3 plus 9, and then divide by 3, you're going to get 6.3. So this 6.3 is the answer when you find the average of those 3. Okay, now you could take another 3. Let's see, let me pick another 3. Okay, 12. Okay, let's do these 3. So let's say I take these 3 out of the bag. So we draw those 3 numbers, then I take the average. The average of those 3 is 8. That's what this 8 is over here. So you can add them and divide by 3 and see you get 8. So every number down here, how is it obtained? By selecting 3 numbers up here and calculating the average. Okay, we take a sample of 3 numbers and calculate the average. And you fill up this bag. When are you done putting things in this new bag? When you've done it for all samples of size 3 that you can draw from this bag. You fill up the new bag. Once you fill up the new bag, you use the new bag to answer the probability questions involving this more complicated experiment. Let's see what it says over here. To find probabilities involving X bar, we need to know what the entire new X bar bag looks like. So you got to make sure you put every possible result of this experiment in here. And you're going to see the same number in there more than once. Like you see the 9.7, for example, is there more than once. That's going to happen because you could get different samples that give you the same average over here. But you got to do it until you fill up the whole new bag. And then when they ask the question, they're going to refer to this bag. They're going to say, if you were to draw 3 numbers out of this bag and take the average, what's the probability you get, the number 6.3? But when you're calculating the probability on your own, you're going to pretend the problem said you're going to draw 1 time out of this bag. What's the probability to get the number 6.3? Okay, so when they phrase it, they're going to phrase it in terms of this complicated experiment. But once you know what the new bag is, you're going to pretend we're drawing 1 side of the new bag and then answer the question. Then it becomes an easy problem. All right, the time has come to do a problem. So let's take a look at this example here. So example 1, I'm starting out with a bag of numbers. Got 4 numbers there. Part A says if a number is drawn out of the bag, what's the probability you get the number 6? Part A says if you draw a number, A means 1. We're drawing 1 number out of the bag. When you draw 1 number out of the bag, the variable is X. It's a pretty easy problem if they say you're going to draw once. Same thing with part B. It says if you draw a single number from the bag, you're drawing 1 number out of the bag, what's the probability it's less than 6? Part A and B will be really easy, but I want to remind you that there's 2 random variables going on in this section. There's X and then there's X bar. When they say you're drawing 1 time, they're talking about the variable X, which means they're talking about the original bag. You don't think about the new bag. But the more interesting questions are the next 2. Part C says if you draw 2 numbers from the bag, what's the probability the average will be 3.5. So let's take a look at part C. It says you're doing these 2 things. You're going to draw 2 numbers from the bag, sample, and then you're going to calculate the average. Remember, X bar stands for sample average. So the problem has to say you're going to take a sample, calculate the average. What's the probability this happens? And that's what it says here. We're going to take 2 numbers out of the bag, randomly select 2 numbers out of the bag and calculate the average. What's the probability the answer we get after we do that is 3.5. So this is an X bar question. So A and B are X questions. C is an X bar question. Sample average. What's the probability of something? Part D, same thing. If we draw 2 numbers from the bag, what's probably the average? It has to say both of those things. Sample average. If you take 2 numbers out of the bag and calculate the average, what's the probability this happens? That makes D an X bar question. Okay, So let's go ahead and look at part A and B first. A and B are much easier, but let's do those real quick. If a number is drawn out of this bag, what's the probability you get the number 6? So the notation for this problem is probability x equals 6. This bag is called x. If it says you're going to draw one number from the bag, they're talking about x. So in the parentheses here, I'm using the letter x, and they're saying what's the probability you get the number 6. So I'm saying if I draw a number out of this bag, one number, what's the probability you get the number 6? All right, anyone know the answer? It's real easy. If you're getting tricked, don't get tricked. This is real easy. What is it? If I draw
1, 4.
1 out of 4, yes. There's 1 6 in the bag, 4 numbers total. Remember, the bottom number is always how many numbers are in the bag total. Top number is how many 6s there are, since I'm trying to find the probability of getting a 6. 1 out of 4. Okay, that's the end of the story on part A. Let's look at part B. Same question, I phrased it slightly different, but if you draw a single number from the bag, what's the probability the number you get is less than 6? Again, we're talking about x. The notation for this question is probability x less than 6. Is everybody with me on the notation? Like less than 6, right? It says, so x stands for the number you get out of the bag. What's probably that number is less than 6. Okay. And again, when they say you're drawing once, the variable is x, not x bar. Okay. And now we got to answer this question. Someone tell me the answer to this.
3 out of 4.
3 out of 4. That's right. Okay. Again, the bottom number is 4 because there's 4 numbers total. Top number is 3 because I have to count how many of them are less than 6. These 3 are less than 6. 3 out of 4. Okay. So again, I'm hoping that's real easy. When you're drawing once out of a bag, I'm hoping the answers are real easy. And all I'm trying to tell you is now that for the stuff we're going to do today, you have to build a new bag first and then pretend you're drawing once out of the new bag. And that's it. Let's go ahead and look at part C and D. Oh, let's take a look at part C. So if you draw 2 numbers from the bag with replacement, what's the probability the average will be 3.5? Okay. Even though we're starting with this bag X, if we're drawing more than once and taking the average, or if we're not drawing once, then you got to make another bag. So I'm going to make a new bag. This new bag, I'm going to call it the X bar bag. X bar. Okay. And here's what I'm going to do. All the results, I shouldn't say different because we're going to see the same result more than once. All the results of doing this experiment, I'm going to put in this bag. So I want to imagine I draw 2 numbers out of here and then take the average. All the different results I can get, I'm going to put in this bag. Someone tell me a result I can get. If I were to draw 2 numbers out of here and take the average, give me a result I could get of that.
2 and 5.
Okay, so I want a final result. Remember, you're going to draw 2 numbers, then you're going to take the average. Like 2 and 5 is the 2 numbers you drew, but now you got to take the average, and then you've completed the experiment. Just take the average of those numbers. What do you get?
A 3.5.
Okay, so for whoever said 2 and 5, like that was the sample, you end up with the number 3.5. So 3.5 is a number in this bag. Now the chat is saying something. I was a little confused. Let me take a look again. Okay, so 1.5 is another thing in the bag because it comes from the sample 1 and then 2. Again, please make sure you understand the whole experiment. It's a 2-step experiment. You first draw 2 numbers. Then whatever numbers you draw, you take the average of them. And whatever the final answer is, that's something that goes in this bag over here. All the final answers, okay? So this doesn't technically go in the bag. This is kind of like your intermediate step when you're trying to figure out what goes in the bag. But these are the numbers that go in the bag. These are the averages you got. So everybody following what I'm saying?
What?
Go ahead.
Yeah. I chose 1 and 5, but the average is 3.
Okay, choose 1, then 5. The average is 3. So 3 would be another thing in the bag. Okay, but I got to do this until I've used all possible samples of size 2 that I can draw out of this bag. So here's how we're going to do this. I'm going to do it again, but I'm going to do it in a more organized way so we make sure we get them all. So here's how it's going to go. Okay, check this out. 1, 1, 1. I'm going to explain what I'm doing right now. I want you to imagine this bag has a bunch of index cards. That's an index card right there, okay? And on one side is the number 1 that's in red, which is like one of the outcomes. But if I'm wondering what sample gave me that outcome, those are the black numbers. It's like the first number I drew was 1, and the second number I drew was 1. Don't forget we're drawing with replacement, so you can get the same number more than once. So imagine on one side it just has the red 1, on the other side it has the black ones, in case I wondered where the red 1 came from. So the red 1 came from the 2 black ones. So that's one sample I could draw. Another sample I could draw is 1 first, 2 seconds. And that would be like on one side of the index card. The average of 1 and 2 is 1.5. And that would be on the other side of the index card. The 1.5 is really what I care about. But I'm letting you know the sample that produced it. Okay, so I drew a 1 first and a 2 second. Okay, let's keep going. So I could also draw a 1 first and a 5 second. If I draw 1 first and a 5 second, the average of those two, you have to add the 1 and the 5, which is 6. Then you divide by 2, you get 3. So the average of those is 3. So if you draw 2 numbers and take the average, these red numbers are the different answers that I can get. Are you guys following me so far?
Yeah.
Okay, I'm going to keep going until I get them all. So this is like all the samples where the first number was a 1. The average of 1 and 6, if you add them and divide by 2, because we have 2 numbers, it's 3.5, is that right? 3.5. Okay, now I'm going to go and write down all the samples that where the first number is a 2. So I could draw a 2 and then a 1. The average of all those numbers is 1.5. Again, all I'm doing is imagining drawing 2 numbers and taking the average. I'm writing all the things that can happen. It's a little annoying, but we got to write it all out. So I could draw a 2 first and a 2 second. The average of those would be 2. Okay. I could draw a 2 first and a 5 second. I can draw a 2 first and a 6 second. The average of 2 and 5 is 3.5. The average of 2 and 6 is 4. So again, I'm just filling up the X-bar bag with all the possible results of doing this. So whatever the experiment is, figure out all the results, put in a bag. Make sure you get them all in there, and you will see the same result in there more than once. That's okay. Let's keep going. So we could have drawn the number 5 first and the number 1 second. The average of those is 3. Again, it's really the 3 that I care about. But if I want to know what sample produced the 3, then those are the black numbers. And I'm putting the black numbers because that makes sure that I get all of them in there. So it could have been, I could have drawn a 5, then a 2. I could have drawn a 5, then a 5. I could have drawn a 5 first, 6 seconds. Or I could have drawn a 6 first, 1 second. 6 first, 2 seconds. 6 first, 5 seconds. And 6 first, 6 second. And that's it. That's all that could be possible if I'm drawing 2 numbers. Those are all the different samples. And if I take all the averages of those, again, this is 3.5. This is 5. This is 5.5. This is 3.5, 4, 5.5, and 6. Okay, so all possible ways of drawing 2 numbers have been accounted for, and then the average after you do that are all the red numbers. So this bag has 16 numbers in it. Now, just a couple things to mention. First of all, whenever they say you're drawing a bunch of times, I want you to pretend, unless they say otherwise, I want you to pretend we're drawing one at a time with replacements. Let's say with replacement here. In the online homework, it's possible they won't say with, if they don't say, then always assume it's with replacement. Otherwise, they could say without replacement. If they say that, you can't get the same number twice. So these 4 would be gone because you can't get 1, 1 or 2, 2 or 5, 5. But most of the time it's with replacement, so you can get the same number twice. Someone asked, how do you count how many things there are in their total? Multiplication rule for counting. You just count all the different samples. You would say the first number and the second number. You have 4 choices for what you select first, or you have 4 choices for what you select second. If you multiply, there's 16. So 16 outcomes in this, 16 things in this bag total. Now, let's go and answer the question. The question says, if you draw 2 numbers from the bag, from which bag? From this bag, and take the average, what's the probability you'll end up with an average of 3.5? That's the question. But you're gonna, so the way they word the question, they phrase it in terms of this bag. But when you actually do the question, you're gonna pretend the problem said, you're gonna draw 1 time out of this bag. And what's the probability you get the number 3.5? And don't tell me the answer yet, but that's how you're gonna treat the question. What I want now is the notation. So it says, what's the probability the average would be 3.5? Let me tell you the notation. The notation is probability X bar. Make sure you put an X bar there if it's an X bar question. It's an X bar question. How do I know? Because again, they say you're going to take a sample, calculate an average. What's the probability you get certain thing? In this case, what's the probability you get the number 3.5? That's the notation for the question. Notation is very important, especially if it's an X bar question. I want to see an X bar in there, so I know you know what kind of problem it is. Okay, now we got to get the answer. Someone tell me the answer to this. Anyone?
2 out of 16.
Oh, close. The bottom number is 16. Top number is not 2. Try again.
4 out of 16?
4 out of 16, yeah. There's 4 3.5s in the bag. 16 total. Yeah. But see, the question was kind of complicated, but after you made the bag, it became very simple. Just how many 3.5s and how many things total. Any questions on part C? Okay, let's look at part D. If you draw 2 numbers, so same thing, we're drawing 2 numbers and calculating the average. What's the probability the average is more than 2? Okay, I want the notation first before we calculate the answer. Someone tell me the notation.
The probability of X bar greater than 2.
Yes. All right, what's the answer? So the bottom number is going to be how many numbers are in this bag total. So the bottom number is going to be 16. And to get the top number, you got to count how many numbers in the bag are bigger than 2 in this bag, in the X bar bag. You just pretend we're drawing ones from that bag. I'm guessing we got an answer in the chat. 12 out of 16, that is correct. 12 out of 16. Because besides these 4 over here, the rest of them are bigger than 2. Yeah, so there's 12 of them that are bigger than 2. Yeah. So see, it went from a problem where you're like, how the heck are we going to calculate that, to not so bad, but yeah, you had to build this bag, which was kind of annoying. But then once you build the bag, pretend you're drawing one side of the bag and then answer the question. Any questions on example 1? Okay. So the concepts in example 1 were super important. I'm hoping it made sense. Now let me say this. Making the X bar bag kind of sucks, right? I mean, we had to do all that work to make the X bar bag. Some problems you're not going to make the bag, some problems you are. I need you to understand how to make the bag so that, you know, if you have to make the bag, you can, but even if you don't have to make the bag to answer the question, you still understand how to make the bag. So I need you to understand how to make the bag. Now, in the online home, I'll tell you on my quiz next time, you're not going to make a bag, okay? And on exams, I'm never going to have you make a bag. But again, I need you to understand the whole story. The story is the most important. Understand how to make the new bag, the X bar bag. So I need you to understand that. And for the online homework, they might give you a few of them where you have to make the bag. So when should you actually draw out the entire X bar bag and when should you not? Well, the answer is if X bar only has 16 things in there, you might as well draw it all out. It's not so bad. But if X bar has like 10 million things in there, don't spend the time drawing out the bag. It's, you know, you're not going to do that. It's going to take forever. basically there'll be more and more things in this bag if the original bag they give you has more numbers in it, and if you're drawing more than 2 numbers. So I just say if things are small, if the original bag they give you is small, like there's not that many numbers in there, and your sample size is small, you're not drawing that many numbers, then I want you to make the bag. Again, that'll be just for the online homework. But online homework is supposed to solidify your learning, so I want to make sure you understand how to build the bag. But on the quiz, what's going to happen is this bag will not have 4 things. It might have 1,000,000 things in there. And we're not going to draw 2 things. We might draw, 80 things out of the bag. Then making this bag would be ridiculous. So what do you do in that case? That's what we got to answer. That's where we're headed, okay? So what do we do when things are big? Okay, when the original bag is big, when the sample size is big, what do we do in that case? That's where we're headed. Before we get there, let's talk a little bit more about example 1. Again, here it just says you're only going to make the entire X bar bag. You're only going to construct the entire X bar bag if the original bag is small, meaning the original bag doesn't have that many things, and the sample size is small, meaning you're only drawing like 2 or 3 numbers out of here or something like that, not too many. In other situations where things are bigger, we're going to have a better way of doing the problem. I shouldn't say better way, but it's actually going to be less work to do it when we have huge amounts of things. Okay. So is everybody, any questions on example 1? Anything up to this point? Any questions? Okay, so one last thing I want to look at on example 1, but I'm going to do this very fast. So there are 2 bags of numbers. There's 2 random variables, and everything we do in section 8.1. You're going to, so what I want to do is I want to find the average of all these numbers that are on the left and the average of all the red numbers over here, okay, in the back. Remember, the black numbers on the right aren't supposed to really be there. They're just there so I can remember what sample produced that average, but it's really the average I care about. And also so I make sure I get them all. Okay, so I list all the different samples so I can see all the averages that we're going to get. Okay, but it's really just the red numbers in the back on the right. I want to find the average of all of them. I want you to think of mu as average of all, okay? So mu sub x means find the average of all the numbers in the x bag, okay? Mu sub x bar means find the average of all the numbers in the x bar bag. This one might look a little bit weird. I get it because x bar is an average and mu is an average. But what I'm saying is your x bar bag, that's the bag that has all the sample averages of size 2, sample size 2 averages. Find the average of all the sample averages. Find the average of all the red numbers. That's what it's saying. And I'm just going to give you the answers so we can move on, because we just need a little result over here. So this is something to know because, again, where am I headed? I'm trying to explain to you what do we do when things are bigger, when we don't draw this bag. So what I would normally have you guys do is find the average of these 4. So you add them up and divide by 4. Then you would add all red numbers here, all 16 numbers, and divide by 16 and see what you get. If any of you did it already, that's great. And if you didn't, I will just tell you the answer. The average of all the numbers in the bag on the left is 3.5. The average of all the numbers in the bag on the right is also 3.5. And it turns out this is always true. In other words, the average of all the numbers in the X bar bag, the average of all the numbers in this bag, is always the same as the average of all the numbers in this bag. We're going to need that later. So that's why I'm doing that now. Okay, so that's one thing. The next thing to do is I want to know the standard deviation of the numbers in each bag. This stands for the standard deviation of all these numbers. This stands for the standard deviation of all the red numbers. And again, to save time, I'm just going to give you the answers. Okay, but on your own, you should get out the standard deviation formula and double check that these answers are right. Let me go ahead and give you the answers. So I got to get it from my phone. Give me a couple seconds here. Okay, so the standard deviation of these 4 numbers, you can put it in the standard deviation formula. The answer will be 2.061552813. You're not going to use the standard deviation formula that I gave you that we usually use, because whenever you have a bag of numbers, we always treat it like population data. Remember, there's two kinds of data, sample data and population data. And when you're finding standard deviation, the formula changes depending on if it's population data or sample data. So if you treat this as population data, that's the one where you divide by n instead of n minus 1, then you get this for the standard deviation of those numbers. If you calculate the standard deviation of the red numbers, you might guess that it's going to be the same answer, but it's not. The standard deviation of all the red numbers is this. Okay. So a couple things to notice. First of all, the standard deviation of the red numbers is smaller than the standard deviation of the blue numbers, or the white numbers, or whatever you want to call these, blue numbers, let's say. Okay. And that should make sense because what does standard deviation do? Standard deviation measures how spread out the numbers are. Well, each red number is an average. And what is an average supposed to do? An average is supposed to tell you, it's supposed to get you closer to the center. So each red number is supposed to be closer to the center of all the numbers than these numbers. So if these all red numbers are all getting closer to the center, then they're all getting closer to each other. That's why the red numbers are closer together. So the smaller spread, they're closer together. But now here's what I want you to do. I want you to get your calculator out. I want you to type this number in. And then I want you to divide the answer by square root of 2. Why square root of 2? Because 2 is the sample size. Okay, so we're drawing, remember we said we're going to draw two numbers out of the bag and find the average. So divide by square root of 2. When you're done, tell me what you get.
1.4577373974.
Yeah, you get this number over here.
Oh, hey, it is.
Right. So that's what I wanted you to notice. Okay. And that gives us another formula. Here, let me write the formulas up here. So we already had this one, mu x bar equals mu x. And the second formula is sigma of x bar is not equal to sigma of x, but if you take sigma of x and divide by square root of n, where n is the sample size, then you get sigma of x bar. These two formulas we will need later. So that's why I'm working on it now while we're in example 1. Questions? Okay, so at this point, we learned a couple of things. We learned what the experiment is in section 8.1. There's a bag of numbers. We're gonna draw some numbers out of the bag, calculate the average. That's the experiment, okay? We got a bag of, it's like a 3-step experiment. We have a bag of numbers. That's the first step, I guess. Then we're gonna draw some numbers out of the bag. That's like the second step. Then we're gonna calculate the average of the numbers we drew out of the bag. That's the third step. And what's the probability this happens, okay? Like you get the number 5 or something like that. And again, the way you would calculate it is you would build a new bag where of all the outcomes of that experiment I just told you, you put all the outcomes in the bag, and then pretend the problem said you're just going to draw one time out of the new bag, and what's the probability you get the number 5 kind of thing. Okay, and that's how you do this kind of problem. Okay, so that's the experiment. And again, you would make the actual bag if things are small. Sample size is small, original bag is small. And then don't forget these formulas, we're going to need them later. But again, where am I trying to go to now? I'm trying to go to what do we do when things are not small? Okay, when this bag is big, when the sample size is big, what do we do? That's where we're headed. All right, let's get there. What is this here? I'm going to skip through this. Let's not worry about it. Okay, but I am going to tell you this story one more time. Okay, so we're still, I've been saying the same story like 100 different ways. I'm going to say it one more time. In section 8.1, here's what's going on. You start off with a bag of numbers. Start off with a bag of numbers. We're going to call it population data. We're going to treat it like it's population data. When you draw one number out of the bag, you get a value of x. In other words, if the problem says you're going to draw one number out of the bag, find the probability of something, they are talking about the x variable. The original bag we call x, and they were talking about the x variable. Also, in section 8.1, they're going to tell you the average of all the numbers in the bag. In a stats problem, you normally don't know that. If it's population data, that's what you would want to know, the average of all the numbers in the bag. Okay. So normally mu is unknown, the average of all the numbers in the bag. But in section 8.1, they're going to give it to you. Because remember, eventually we're trying to guess mu. And I've told you your best guess is x bar. You take a sample, calculate x bar. X bar is your best guess for mu. And first day of class, I told you X bar is supposed to be close to mu, okay? But now we're trying to investigate how close to mu is it supposed to be? What's the probability it's within, 2 from mu? What's the probability it's really far from mu? So that's what we're trying to figure out, probabilities involving X bar. So just for section 8.1, they're gonna actually tell you what mu is. So the original bag that they give you, they're gonna tell you mu, the average of all the numbers in the bag. They're also gonna tell you sigma, which is the standard deviation of all the numbers in the bag. And we're gonna investigate the behavior of X bar. We're gonna answer probability questions involving X bar. Okay, but again, after today, these will not be given. The whole goal is to figure out what they are. Okay, and then we're gonna form a new bag. The new bag is called X bar. Remember, every problem's got 2 variables, X and X bar. If the problem just says you're doing something once, you're drawing once out of the bag, they're talking about the X bag. For the X bar bag, if they say you're gonna do something a bunch of times and take the average, then they're talking about the X bar bag. Just keep remembering that X bar is sample average. So if the problem says you're gonna take a sample, calculate an average, then they're talking about X bar. And here's how you form the X bar bag. What you do is you take a sample of size n from the original bag, calculate the average. That average is called X bar. And you can do this over and over again for all possible samples of size n that you could possibly draw from the original bag. And this will give you a new bag, the X bar bag. And then let me click through some of this. And then again, when they ask questions involving X bar, they're gonna ask it the more complicated way. They're gonna say, if you draw a sample of size n from the original bag, the one they give you in the problem, and calculate the average, what's the probability something will happen? But again, when you're trying to figure out the answer, you need to imagine the X bar bag and just pretend the problem said, you're gonna draw one number from the X bar bag. What's the probability this happens? Okay, so they word it this way in terms of the original bag, and it's more complicated to word it because it's like a 2 or 3 step procedure. But you're gonna pretend you have the new bag constructed and you're gonna draw one time out of the new bag. What's the probability this happens? Here's a picture. So again, we start off with the original bag of numbers, call it X. Think of it as population data. And again, in section 8.1, mu and sigma will be given to you. Even though they're usually unknown, they're gonna be known in this section. So mu is the average of all the numbers in the bag. Sigma is the standard deviation of all the numbers in the bag. Those are gonna be given. And again, the question is gonna say you're gonna take a sample of size n and calculate the average. What's the probability something happens? So in order to answer that question, you have to figure out what are all the outcomes of this experiment and put it in a new bag. And the new bag is gonna be called X bar. So you take a sample of size n, calculate X bar, put the answer in the new bag, the X bar bag, and do this for all possible samples of size n. One more time, each number in this bag is an average of a sample of a certain size drawn from this bag. Like maybe I take these 4 numbers, add them up, divide by 4, and I get a certain average. Then take another set of 4 numbers, find the average, maybe you get some other thing, kind of thing. You do this until you've run out of samples you can draw from here of size n, and then you fill up this bag. The new bag has all sample averages in it, and taking a sample of size n and calculating X bar is equivalent to drawing one number from the new bag. So one more time, the problem is going to say you're going to take some numbers out of here and find the average. You're going to take a sample of size n and calculate the average. What's the probability you get this thing to happen? But when you're answering the question, you're going to pretend the problem said you're going to draw one time out of this bag. What's the probability you get a certain thing to happen? Okay. All right, I guess we got to go through this slide. So it says there's 3 different ways to draw a sample of size n from a bag. Okay, if I said, I want to figure out the average age of all Rio Hondo students. And the way you're going to do it is I select one of you and I say, let's say we're on campus, okay? And I say, go outside, go talk to 100 students and get their ages and come back. How would you do that? Well, would you select them one at a time with replacements? Would you select them one at a time without replacements? Or would you select them all at once? I mean, how are you going to select the 100 students? Well, you probably wouldn't do it this first way, because if you select them with replacement means you can select the same person twice. So you probably wouldn't go up to a person and say, how old are you? Write it down, and then go up to the same person later on and say, how old are you? Because you already talked to that person. You probably wouldn't do that twice. you probably would do it this way. You just talk to 100 different people is what that means. And you might do it one at a time, like find one student, ask their age, and find another student, ask their age, and do it until you've done it 100 times. Or maybe you get lucky and you find 100 students standing in some area on campus and you just get them all to tell you their age kind of all at once kind of thing. When you select a sample in real world stats problems, usually you do it this second way or this third way. But the math we're going to develop is we're going to be assuming the first way. So you might say, Greg, that doesn't make sense. You're going to make up formulas for doing something one way, but we're always going to do it the other way. How does that work? And the answer is, it doesn't matter how you take the samples. As long as a certain condition is true, if you draw the sample any of these ways, you're going to get basically the same probabilities for X bar. So all the formulas that we're going to get for the rest of the semester are going to be fine, as long as a certain condition is met. That's what it says over here. When we draw samples, we will always think of them as drawn the first way with replacements. But as long as this condition is met, which I'll talk about in a second, then all probabilities regarding X bar are going to be essentially the same. So in other words, when you're doing problems from now on, don't worry about if it says with replacement or without replacement. When we're dealing with big numbers, okay, don't worry about it if it's with replacement or without replacement. The answer is going to be essentially the same. So in case you're worried, don't worry is what that's saying. Let's go ahead and take a look at this condition. What does this condition say? Little n less than or equal to 0.05 times big N. Little n is your sample size, and capital N is the population size. So what this says is as long as your sample size is less than or equal to 5% of the population size, then I don't really care which way you drew the sample. All the probabilities involving X bar are going to be the same. For example, if I want you to guess the average age of all Rio Hondo students, then this capital N would be how many Rio Hondo students there are total, which is 20,000. If you do 20,000 times 0.05, you get 1,000. So if you multiply this, you get 1,000. So as long as your sample size is less than 1,000, then I don't care how you drew the samples. So if you're only going to talk to 100 students, that's less than 1,000. So then you're good. Anyway, I'm not going to say much more. I'm not going to have you check this thing, but in the online homework, they may have you check that condition. So I want to make sure I mentioned it. And again, if you're doing problems and you're like, wait a minute, is it with replacement or without replacement? All I'm telling you is it doesn't matter. When things are big, it doesn't matter. Okay. So we're still trying to answer this question. How do you find probabilities involving X bar when the sample size is bigger? Okay. So again, example one, we did example one, and we actually constructed the X bar bag. We actually built the bag. But what do you do when things are bigger and you're not willing to build the bag because the bag has got a gazillion things in it? What do you do? And that's what we're going to analyze in the next couple of slides. What does the probability distribution of X bar look like? Okay, so I'm going to start you out with another bag. We're going to suppose we have a bag with the numbers 1, 2, 3, 4, 5, 6 in it. And we're going to look at 3 random variables. We're going to look at X. Remember, X is the number you get when you draw once out of the bag. We're going to look at X bar 2. X bar means sample average, but I'm putting the little 2 there to remind you that we're going to take 2 numbers out of the bag. So for this example, we're going to take 2 numbers out of this bag and calculate the average. But then we're going to change the sample size to 3, and we're going to look at X3 bar, which is the average of a sample of size 3 drawn from the original bag. Okay, so we're going to draw once from the bag. We're going to draw twice and take the average. We're going to draw 3 times and take the average. And I want to see what the probability distributions of these bags look like. Here's the original bag here that I'm starting out with. So it's got 1, 2, 3, 4, 5, 6. This is a discrete random variable. In chapter 6, we would make a table or we would draw a histogram. I decided to draw a histogram here, so we have a picture. So this is the probability distribution. Remember how it works. The numbers on the bottom tell you all the numbers that are in the bag. Those are all the numbers that can be drawn out of this bag. And then above each number, we put a rectangle. The height of the rectangle is the probability of drawing that number. The probability of drawing the number 1 out of this bag is 1 out of 6, so the rectangle is drawn at a height of 1 out of 6. But that's the same for all of them. The probability of drawing a 2 is 1 out of 6. The probability of drawing a 3 is 1 out of 6. They're all 1 out of 6. So the histogram or the probability distribution looks like this for the original bag. But again, it's not the original bag I care about. It's X bar what I care about. So before we look at the next slide, I want to think about what does the X2 bar bag look like? All right. Again, what does X2 bar mean? It means we're going to draw two numbers out of here and calculate the average. Somebody give me a result if I take two numbers out of here and calculate the average. What could an outcome be or a result?
1.
Okay, 1. Tell me how you got the 1. Okay.
You know
So-
what? I think I did it, but I did it with replacement. I did 1 + 1.
Yeah, that's all I want you to tell me. Yeah. So you drew the 1 the first time, you drew a 1 the second time, and the average is 1. That's all. You're right. I just wanted you to say it. Yeah. Okay, so 1 is in the bag. To be more clear, the sample was a 1 and then a 1, and then the app. So here, I'll make a little table just for fun. So the sample and then the average. Okay. So your sample was 1 first, 1 second, and the average is 1. 1 + 1 divided by 2 is 1. Somebody give me another number that goes in this bag. Another number. So again, what are we doing? We're taking two numbers out of here and calculating the average. When you're done doing all that, give me a possible final result.
1.5.
Okay, 1.5. Tell me how you got that. Like what sample gave you that?
1 and 2.
Okay, so that would mean like the first number you drew was a 1, the second number you drew was a 2. But the number 1.5 is in there twice because you could have drawn the number 2 first and number 1 second. That would also give you an average of 1.5. So are we following what I'm saying?
Yes.
Okay, someone give me one more average you could get. One more, if you take two numbers out of here and calculate the average, what's another result you can get?
5 from 6 and 4.
Okay, so you're saying there's a 5 in here, and you can get that by 6 and 4. Okay, and actually the number 5 is in there 3 separate times because you can get it from 5 and 5, meaning the first number you draw is 5, second number you draw is 5, the average is 5. Or you could have drawn the 4 first and the 6 second. So actually 5 is in there 3 times. But anyway, if you write down all the samples and write down all the averages and put them in this bag, I'm not going to spend the time doing it right now. There would be 36 different things in there. But if I, it'll only take a couple minutes to do it, but I'm not going to do it. But that's the idea. That's what the X2 bar bag looks like. Now here's a picture of the X2 bar bag. Again, just like you said, there's a 1 in there, 1.5 is there 2 times. 5 is there 3 times. I didn't list it, but like this would be a 5. This would be a 5. This would be a 5. And if you make the probability distribution for this, the picture would look like this. All these numbers down here are all the numbers in the X2 bar bag, meaning if you took two numbers, I'm going to draw the X bag over here just to remind you. If you took two numbers out of this bag, and calculated the average, then these are all the different answers you could get if you do that. Okay. And notice some rectangles are higher than others because some numbers can come up more than once. Like the number 1, the probability of, if you draw two numbers out of here and calculate the average, which is equivalent to drawing one number out of here, the probability you get a 1 is 1 out of 36. There's only one 1 in the bag, and there's 36 things total if you were to make the entire list. So this rectangle is drawn at the height of 1 out of 36. If you draw two numbers out of here and calculate the average, what's the probability get the number 1.5? That's equivalent to drawing a 1 out of here and getting the number 1.5. The probability is 2 out of 36. There's two 1.5s, 36 things total. And then for the probability getting a 2, you can see there's 3 2s. So 3 2s, 36 things total. So that rectangle has a height of 3 out of 36, which is just above 0.08. And anyway, if you do this, if you make the entire bag and make the entire probability distribution, you get a picture like this. Okay, now what I want to do, we were drawing 2 numbers there. Now I want to draw 3 numbers. So I'm going to go back a couple slides. And I want to talk about the X3 bar bag now. Again, what does X3 bar mean? It means we're taking 3 numbers out of here and calculating the average. And I want to know what kind of things go in there. Somebody give me something that goes in there. Just any number that would go in here.
1, 2, and 3.
Okay, I need a final result.
An
After-
average of 2.
So 2. Okay, 2 would go in there. Yes. 2 is the final result if your sample was 1, 2, 3. Yes. That means you drew the number 1 first, drew the number 2 second, drew the number 3 third. The average of those numbers is 2. You add them up, you divide by 3 because we have 3 numbers. And the number 2 is going to be in there a lot because here's another way to get a 2. I'm just going to mix the numbers around. All of these have an average of 2. Also 2, 2, 2 has an average of 2. Also, what else has an average of 2? 1, 2, let's see. Oh, we already did 1, 2, 3. Oh, that might be it. Well, how many is that? 1, 2, 3, 4, 7 of them. So the number 2 will be in this bag 7 times. Why 7 times? Because there's 7 different samples that gives you an average of 2. Is everybody following what I'm saying? Oh, there's more. It's not 7. There's also 1, 1, 4, 4, 1, 1, 1, 4, 1. Oh, there's 3 more 2s. This bag would have 10 2s in there. So there's 10 different samples that give me an average of 2. Can someone give me another average that's in the bag besides the number 2?
Five.
5? Okay.
Yeah.
Tell me how you can get a 5. Tell me how you got the 5.
6 plus 4 plus 5.
Okay, your sample could be 6, 4, 5, and the average is 5. And again, there's lots of ways to get an average of 5. So there's lots of ways. There's gonna be a lot of 5s. But again, I want you to understand every number here, how was it obtained? You took 3 numbers out of here, calculated the average, and threw the answer in this bag. If you do this for all possible samples, there's gonna be 216 different ones when you're done. So it's gonna take some time. But I'm just gonna show you the picture here. This is what the X3 bar bag looks like, and here's what the probability distribution looks like. Here's the original bag, X again. Remember, the original bag is the bag 1, 2, 3, 4, 5, 6. If you take 3 numbers out of this bag here, and calculate the average, these are all the different answers you could get. Some of you said 2, some of you said 5, right? But there's other ones. There's all these other ones you could get. And to find the probabilities, you'd have to actually make this entire bag, which I'm not showing you the whole bag. But again, I did this once. It was very annoying. But I listed all 216 of them out so I could figure out what the probability distribution looks like. And the probability of getting a 1 is 1 out of 216. There's 1, 1, 216 things total. As far as the 1.3, the number 1.3 is there 3 times. The probability of that was 3 out of 216. The number 1.7 was there 6 times. So the probability of that was 6 out of 216. And I just figured out all the probabilities of each individual outcome. I made this picture over here. All right. Now, what we want to investigate is what the shape looks like as the sample size increases. So, oops. So this is the original bag here. There's the probability distribution. I know it's a histogram, but if we treat it like a continuous random variable where there's like a curve, then it's kind of like uniform distribution. It's like flat, like all the rectangles have the same height. So it's like a uniform distribution, horizontal line. If I connect like the tops of all the rectangles and treat it like it was a curve, it would be like a horizontal line there. That's the original bag. Now, if we go to sample size 2 and you look at the picture and you connect the tops of all the rectangles to try to make some kind of curve out of this, it looks kind of like a triangle now. If I had to describe the shape of the histogram, it's like a triangle. It goes straight up, then straight back down. If we change the sample size to 3, well, what's the shape of this look like to you? Take a look. What's the shape?
Normal bell.
Looks like a normal distribution. Yeah. That's what it looks like. And that is the big result of section 8.1, okay? Basically, the whole point is when things get big, how do you find the probability? You do a Z transformation because the curve, the probability distribution looks normal. Looks like a normal distribution. So again, it takes us back to section 7.2. Every problem we're going to do for the rest of the day is like a section 7.2 problem. Okay, here we go. Central limit theorem. It's called the central limit theorem, most important theorem in all of stats. I will ask you for sure on the next quiz, state the central limit theorem. On the next exam, I will for sure ask you, state the central limit theorem. On the final, I will for sure ask you, state the central limit theorem. So at least 3 times in this class, I'm going to ask you to state the central limit theorem. So be prepared to state the central limit theorem. And let me tell you what you're going to write. Well, you don't have to write this first thing down. This condition you don't need to write down. But you're going to write down these 3 bullet points. Here's what the central limit theorem says. Remember, there's 2 bags, okay? There's the X bag, which is the bag that they give you, and there's the X bar bag that you construct. The conclusion of the central limit theorem is under certain conditions, this bag has a normal distribution. That's the conclusion. It's all about X bar. It has a normal distribution. That's what you got to remember, okay? The first bullet point says, this bag can be anything, but as long as the sample size is big enough, this bag has a normal distribution. So let's go ahead and read what it says here. If X is any random variable whatsoever, it's like if X is any starting bag whatsoever, as long as the sample size is greater than or equal to 30, the X bar bag has a normal distribution. Okay, a couple things to tell you. First of all, central limit theorem is always about X bar. So the conclusion is that X bar has a normal distribution. Sometimes students say X has a normal distribution. No, no, no. This central limit theorem is about X bar. X bar has a normal distribution. But X bar comes from X. The second bag comes from the first one. So what we're saying is we don't care what the first one is. The second one, the X bar bag, has a normal distribution as long as n is greater than 30. Where'd the 30 come from? Well, it's a rule of thumb. That's the rule we're going to go by. As long as the sample size is greater than 30, X bar has a normal distribution. You saw in the pictures we drew earlier that even when n was 3, when our sample size was just 3, it already looked normal. But the rule of thumb is going to be 30. So as long as the n is greater than 30, then it doesn't matter what the original bag is, new bag is normal. That's the first thing you're going to write, okay, this bullet point over here, when I ask you to state the central limit theorem. The second part of the central limit theorem says, if X is normal, meaning the original bag is normal to begin with, then the new bag is normal, and I don't care what the sample size is anymore. So again, if the original X bag has a normal distribution, then the X bar bag has a normal distribution as well, and it does not matter at all what the sample size is anymore. So that's the second thing you're going to write down when I say state the central limit theorem. And the third thing is going to write down these 2 formulas that we saw earlier. We need these formulas because how do you do a problem? So if we're doing an X bar problem and it has a normal distribution, how do you do normal distribution problems? You do a Z transformation. We do Z transformation, what do you have to do? You have to minus mu divided by sigma. What mu, what sigma? This mu, this sigma. So that's why I need these formulas. So when I ask you to state the central limit theorem on the next quiz and in the future, you're going to state these 3 bullet points. A lot of people forget the formulas. Don't forget the formulas. And here's a little picture of the situation. It just says this is like a picture of the distribution of the original bag. It does not matter what it looks like at all. The distribution of X bar is going to be pretty and normal. Basically, that's the idea there. All right, the results have been told to you. Now all is left to do is to do a few problems. Let's go ahead and read what it says here. A bag of numbers has a normal distribution with a mean of 10 and a standard deviation of 4. Find these probabilities. Now, part A, B, and C says we're drawing a single number. Remember, in this section, there's two variables, X and X bar. When they say you're drawing one number, we're talking about the variable X, okay? But then if you read the next 3 parts, it says we're going to take a sample of size 20 and calculate the average. Sample average. When you see that, what variable are we talking about? When it says single number, we're talking about X. When we're taking a sample and calculating an average, what variable are we talking about? Whenever it says sample average, they're talking about the X bar bag, X bar random variable. Sample average, that's what X bar is. Sample average, that's the X bar bag. Okay, so remember, every one of these problems, there's two variables. There's x and x bar. When is it x? If we're doing something once. If we're drawing once from the bag that they give us. If they say we're drawing many times and taking the average, that's the experiment we've been focusing on today. That's the x bar random variable. All right, so I'm going to do, okay, what are we going to do? First of all, when you do these problems, there's going to be some writing you're going to have to do at the beginning. You're going to have to write some stuff about x and some stuff about x bar. Let me go ahead and write it down. So you can write down x. X is always the number you get when you draw one number from the bag. This is the number you get when you draw one number from the bag. I know there's two bags, but there's only one bag that they give you. The other one you construct, at least in your head. Now the problem, this problem says that the distribution of this bag is normal. It says a bag of numbers has a normal distribution. So this distribution is normal and it's given. They tell us that. They also tell us the average of all the numbers in the bag and the standard deviation of all the numbers in the bag. There's going to be two mu's and two sigmas. So this is mu x and sigma x because they both have to do with the x random variable. Mu x is 10, sigma x is 4. Okay, so you got to write that down. Then you're going to write down the corresponding things for x bar. X bar is always a sample average. This is the average of a randomly selected group of 20 numbers drawn from the bag. How do I know 20 numbers? Because if you go and read parts D, E, and F, they all say we're sample size 20, sample size 20, sample size 20. Okay, then you got to write down the distribution for this one. It's also normal. You're going to have to write down y. Central Limit Theorem says there's two different situations where this one is normal. This problem, the sample size is 20. That's not greater than or equal to 30. So that's not why this is normal. The reason this distribution is normal is because this one is normal. That's the very first, no, that's the second bullet point for the central limit theorem. If x has a normal distribution, then x bar has a normal distribution, and I don't care if the sample size is bigger than 30 or not. Okay, so that's what's happening here. So normal distribution. So you can write down normal distribution. This is, and you can write down y. This is by the central limit theorem. CLT stands for central limit theorem. Because x is normal. Because this one is normal over here. And then you're going to write down the mean and standard deviation for x bar. The formula for mu of x is that it's equal to for mu of x bar is that it's the same as mu of x. So mu of x bar and mu of x are the same. So this mu is also 10. But the sigma of x and sigma of x bars are not the same. The formula is sigma of x over square root of n. Sigma of x here is 4. Divided by square root of n. N is 20. Now this number is an ugly number. I don't want you to do any rounding, so let's leave it like that for now. Okay, so you got to write all this stuff down before you start the problem, right? Everything there is to know about the x variable, everything there is to know about the x bar variable, and then you do the problem. Let's go and do, okay, let's do part A. What's the probability the single number drawn from the bag is less than 20? We're drawing a single number. Are they talking about x or x bar when they're talking about drawing one number?
X.
They're always talking about x when they're talking about one number. So the notation is probability that the number you get when you draw one number is less than 21. Okay, because x is normal, it's a normal distribution question. What do? You do z transformation. Z transformation. Remember, you only do z transformation when your variable is normal, but both of our variables are normal in this section, in this problem. So you do z transformation. All right, check out how the notation is going to go. It's x minus, you're supposed to write mu, but you can't write mu this time because there's two mu's. Which one is it? if we're doing an x problem, it's mu of x. So you're going to put mu of x over sigma of x. This side, 21 minus mu x over sigma x. The part that had the x, that whole mess turns into z. And for the right side, 21 minus, all right, what's mu x?
10.
10. Sigma x is what?
4.
4. Yeah. And you calculate this on the calculator. .75. And then you just do the z problem, probably z less than 2.75. Do I have a z table here? Yeah. 2.75. If it's a less than, you just look it up in the table. 2.7 is here. The 5 is here. You go like this and like this. And the answer is 0.9970. This problem, this part A, is no different than stuff we've done before. Basically, they're saying it's normal, find some probability, and be done with it. Any questions on part A? Let's go to part B. Let me double check one thing here. Yeah, part B is okay. All right. So it says this, so we have to decide first, which variable are they asking about? Are they asking about x or x bar? Find the probability a single number drawn from the bag is larger than 5. Single number. We're drawing one number. We're not taking a sample and calculating an average. We're drawing one number. What variable are they talking about? X or x bar?
X.
They're talking about x. When you're drawing one number, they're talking about x. Find the probability a single number drawn from the bag is larger than 5. The notation is probability x greater than 5. Okay, now how do you do this problem? Well, if we go back a couple slides, it says x is normal. If it's normal, what do you do? If you want to find a probability, you do z transformation. So that's all it is. All the rest of these problems are z transformation problems. Z transformation. So it's going to be probability. Now look at how I'm writing this. It's going to be x minus, you don't just write mu because there's two mu's. You write mu of x because this is an x problem divided by sigma of x greater than 5 minus mu x over sigma x. Okay. Now the one that has the x in it, that whole mess turns into z. And for this side, I'm going to plug in the numbers for mu x and sigma x. Let me go back. Here they are. Mu x is 10, sigma x is 4. This whole part that we're doing is this side, x variable. So 10, 4. So let's go back here. So 10 here, 4 here. And this is negative 1.25 if you calculate that on the calculator. Now, to do a z problem when it's a greater than, you do 1 minus probably z less than the number. And then when it's a less than, you look it up in the z table. It's a negative number, you're going to look it up in the negative side of the z table. Negative 1.25. So negative 1.2 you look for here. Last digit 5 from on top. And you go like this and like this. The answer is 0.1056. Okay. You subtract those answers, you get 0.8944. That's the answer to part B. Now this problem is exactly like section 7.2. Actually, there's nothing new here, okay? But then it becomes new when we're talking about an X bar problem. So let's go forward to part, let's go and do part D. Again, it says, find the probability in a sample of size 20, the average is less than 9.5. They're saying you're going to take a sample of size 20 and calculate the average. What's the probability that average is less than 9.5? Are they talking about the X random variable or the X bar random variable in this question?
X bar.
Talking about X bar. Okay. The notation would be probability X bar less than 9.5. Now, look, when it's an X bar question, I'm going to be looking at the notation carefully. If you don't put the X bar, I'm going to go, did they know it was an X bar question or not? Okay, so make sure you put X bar. That lets me know you could tell that it was an X bar question. Then, how do you find the probability involving X bar? Well, Central Limit Theorem says X bar has a normal distribution. Let's go back a few slides here. Okay, right here on the right side, we're doing an X bar problem. X bar has a normal distribution. So again, to find the probability, you do a Z transformation. All right, so let's go ahead and do a Z transformation. Watch how I write it. Probability is X bar minus mu of X bar. Again, if it's an X bar question, you can write mu of X bar there. And then down here, sigma of X bar. Less than 9.5 minus mu X bar over sigma X bar. Now, the one with the random variable X bar, that whole mess is going to turn into Z. And on this side, you're going to plug in the numbers for mu X bar and sigma X bar. Mu X bar, the number is 10. Sigma X bar, people get this one wrong a lot. They put the number 4. It's not 4. One reason they get it wrong is they go, oh, mean is 10, standard deviation is 4. They read from the problem. But this 4 is sigma of X, not sigma of X bar. Let's go back a few slides to here. You have to put these numbers for mu X bar and sigma X bar. Now, if you get the mu X wrong, you'll be okay because they're 10 both times. But the sigma depends on if it's sigma of X or sigma of X bar. So again, that's how I'm going to know for sure if you get it or not. If you put a 4, you don't understand what's happening, and then you're going to lose a lot of points. If you put 4 over root 20, then you like, yeah, you know it's a X bar problem, then you'll be good. So this is the mu X bar. This is the standard deviation of X bar, 4 over root 20. So let's go forward here. So the bottom again is not 4. Very common mistake. It's 4 over root 20. Just use sigma X bar that you wrote at the beginning. Okay. Once you get that, now you got to calculate this. One last thing to tell you here. Okay, here, let me type this in. So 9.5 minus 10, I'm getting the answer. Now, divide. Here I'm dividing by a fraction. It's another place where students make mistakes. So here's some advice. When you divide by a fraction, my advice to you is before you type any part of the fraction in, open some parentheses. If I were you, I would open 3 parentheses. Students stubbornly don't do this, but just open a parentheses and you're going to get the right answer. Open some parentheses before you type 4 over root 20. Then you do 4 divided by square root of 20, and you should be good. On my calculator, I'm getting negative 0.559, whatever. If you round it to 2 numbers after the decimal, it's negative 0.56. So if you got negative 0.56, you're good. If you didn't get that, then the number you would have got if you typed it in wrong is negative 0.02795, whatever it is. If you get a number like this, you type this in wrong. How do you make sure not to type it in wrong? Open some parentheses before you type 4 over root 20. Anyway, if you got negative 0.56, you're in good shape. If you didn't, then put the parentheses first, and then you get that. Now it's a Z problem, and it's Z less than something. Z less than something, you just look it up in the table. So I have to look up negative 0.56 in the table. It's negative, so we're going to use the negative side of the Z table, negative 0.56. This number here, negative 0.5, we look for it on the left column, which is right here, negative 0.5. The last digit, 6, from the top over here. And then you just go to the right on the negative 0.5, and you go down from the 0.06 until these lines meet. They meet at 0.2877. And that's the answer to that one. Let's go and do part E. Okay. What is the probability that in a sample of size 20, the average is at least 11.3? Okay. Are they talking about the variable X or the variable X bar here?
X bar.
X bar. They're saying we're going to take a sample, calculate the average. What's the probability the average is at least 11.3? All right, who can tell me the notation for this? So probability, come on guys, help me out. Probability what?
probability that x is greater than or equal to 11.3?
X bar.
X bar, yeah.
That's very important. That's the whole point. X bar, sample average. So make sure you put X bar. Greater than 11.3. Now you might say, does it have to be greater or greater than or equal to? It does not matter because it's normal. Okay? It's not like it's binomial and you have to worry about that. It's normal. So you can put greater than or greater than or equal to, it doesn't matter. Okay, is everybody with me on the notation?
Yeah.
Okay.
Yes, sir.
And again, from the earlier slide, it said X bar was normal, so you do Z transformation. Watch the notation here. It's going to be X bar minus mu of X bar. If it's an X bar problem, put mu of X bar there. Down here, you're going to put sigma of X bar. On the other side, same thing, 11.3 minus mu of X bar over sigma of X bar. Okay. And then the part that has the X bar, this mess will turn into Z. The other side, 11.3 minus. Now, sometimes people will forget the X bar and they'll put X. Yeah, you'll lose points. But this part over here is going to let me know for sure if you get it or not. What do you put for mu of X bar? What do you put for sigma of X bar? Mu of X bar is 10. Let me go back a few slides. Mu of X bar is 10. But mu of X is also 10. So if you put the wrong one, you're still going to get the right answer because it's 10. Or if you're looking up on top and you see mean of 10, you might put 10. Okay. But when you put the standard deviation, very often people will put 4 because the 4 is the number that's in the question. But that's sigma x, and I'm not asking about sigma x. I'm asking about the variable X bar. This is what we're going to put for the standard deviation. 4 divided by square root of 20. So if you put 4 over root of 20, then you're getting it. If you only put 4, then it's disaster. You're probably going to get a 0 on the problem at that point. So make sure you put the right sigma X bar. So 4 over root 20. So if they're talking about X, you just put 4. But if they're talking about X bar, you're going to put this 4 over root 20. Let's go forward. 4 over root 20. Is everybody with me on that much?
Yeah.
Yes.
Okay,
Yes.
next part. When you're calculating this, I'm going to tell you, people have trouble calculating it. This is what you do, 11.3 minus 10, get the answer. When you divide by a fraction, listen to what I'm saying. My advice to you is push divide. Before you type the fraction, open some parentheses. I would open like 3 parentheses on the calculator. So that's what I'm doing, opening 3 parentheses. I'm going to type 4 divided by square root of 20. So there's a couple of things that you can run into calculator issues with. One of them is when you divide by a fraction. Okay, so again, get the top answer. After you have that answer, push divide, open a bunch of parentheses, and then type 4 divided by root 20. When you get your final answer, you have to round to 2 numbers after the decimal place. It's 1.45. If you got that, then you typed it in right. If you got something totally different, like, let me see, what would it be? So the only other answer that you could get, I guess, would be 0.07. So if you got a 0.07 here, then you typed it in wrong. Okay, so okay, 1.45. Any questions? Okay, then how do you do a probability Z greater than problem? You can use the 1 minus formula. 1 minus probability Z less than 1.45. And the Z less than 1.45, you can look up in the table. 1.45. Here's 1.4. Here's the 5. 0.9265 for that one. And you got to do 1 minus that. So the final answer is 0.0735. That's part E. Questions on example 2, part E.
I guess it's like a leftover question from the last section we did, but how come we're doing Z is greater than and not Z is greater than or equal to?
Doesn't matter.
Okay.
Doesn't matter because this is a continuous random variable. In this section, the result is X bar is normal, and normal is continuous, so it doesn't matter.
Gotcha. Okay.
Okay, so that's all of example 2 that I'm going to do because I have more examples to do. But let's go ahead and move on. That's the story for example 2. In example 2, I want you to notice that they told you about the original bag. The original bag was normal. Because they told you the original bag is normal, I can ask you questions about the original bag. If they don't tell you anything about the original bag, then we can't ask questions about the original bag. But I can still ask questions about X bar because the first part of the central limit theorem says X bar is still normal no matter what the original bag is. And that's what's happening in example 3. Let's take a look at example 3. Example 3 is very similar to the kind of question you'll get on a quiz because it has a context. The only difference between example 2 and example 3 is they don't mention a bag of numbers, but there is a bag of numbers and the numbers have a meaning. Let's go ahead and read what it says here. The amount of credit card debt among all Americans ages 18 to 24 has a mean of 2,982 and a standard deviation of 315. What is the probability that in a random selected group of 36 Americans between the ages of 18 and 24? So let's go ahead and do, I guess we'll do part B. Okay, let's find the average, probably the average credit card debt is more than 2,850. Okay, just like example 2, there's 2 random variables here. There's X and there's X bar. But in the last problem, they said the original variable, X, has a normal distribution. And then they said the mean and the standard deviation. This time, they say the amount of credit card debt has a mean, this mean and this standard deviation, but it doesn't say has a normal distribution. If they don't say X has a normal distribution, then they can't ask you a question about X. They can still ask you about X bar though, because X bar always has a normal distribution basically under the right conditions because of central limit theorem. So these 3 questions are all X bar questions, not X questions. And again, how do I know that? Well, in order for it to be an X bar question, you need to see sample average in the problem. The problem says, what's the probability that in a random selected group of 36, there's a sample right there. We're selecting 36 Americans. What's the probability their average credit card debt? Sample average. What's the probability? It's more than this. Sample average. That's an X bar problem. And all 3 of these are X bar problems. Now again, we have to write down a lot of stuff at the beginning. So we still have to write down what X is, even though they're not asking us any questions about X. X is always the answer you get when you draw 1 time from the bag. I need you to imagine that every American that's between 18 and 24 wrote down their credit card debt on a piece of paper and put in a bag. That's the original bag of numbers we have. If you put your hand in the bag and draw 1 time, it's like you selected 1 number from this bag. So X is the credit card debt of 1 person, of A means 1, of a randomly selected American between 18 and 24 years old. Okay, so it's the credit card debt of 1 person. If you ask 1 person, that's X. The distribution is not given to us in this problem, so I'm just going to write unknown. But they still tell us the average of all the numbers in this bag. The average credit card debt is, what is it, 2,982. I'm going to leave the $sign off. And standard deviation is $315. That's what they tell us about this original bag. So again, there's a bag of numbers here. They just didn't say it. But it's like the credit card debts of all these people put in a bag. Now you're going to write down the X bar variable. X bar is always sample average. You write the average credit card debt of a randomly selected group of 36 Americans between the ages of 18 and 24 years old. Okay, The distribution for X bar is normal. It's always going to be normal because how are you going to do it if you don't know what it is? Central limit theorem says it's going to be normal under certain conditions. It's not because this is normal. In example 2, X was normal and that made X bar normal. This time X is not normal. What's the reason that the distribution of X bar is normal this time? Does anyone know? So the reason is because in this problem, the sample size is 36 and that's greater than 30. That's the first bullet point for the central limit theorem. It says if n is greater than 30, then X bar has a normal distribution. So you're going to write down it's by the central limit theorem again, but this time it's because n is a number greater than 30. Okay, then I need to know what mu of X bar is and what sigma of X bar is, and then we could do this problem. Mu of X bar, again, the formula is that it's equal to mu of X, so it's equal to the same mu over here, 2982. But the standard deviations are not the same. The formula for sigma of X bar is it's equal to sigma X over square root of n. Sigma of X is 315, square root of 36. Now, this time, this number is actually a pretty number. If you type it in the calculator, it doesn't go on forever. So I'm going to go ahead and type it in. 315 divided by square root of 36. I'm getting 52.5. That's not rounded. It's exact. I don't want you to round it all until you have to. So in the last problem, this fraction went on forever, so I didn't have you write it out because I don't want you to round it. But if it's a pretty number like 52.5 and it just stops, then you can go ahead and write down the whole thing. All right, so you write that stuff down at the beginning. And now we're going to go do a part of the problem. I'll skip part A. We'll go to part B. Part B says, find the probability their average credit card debt is more than 2850. Again, it says, what is the probability that in a random selected group of 36 Americans, so we got a sample, that their average credit card debt, sample average, is more than 2850. What letter are they talking about? X or X bar? Okay, so when it says sample average, they're talking about the letter X bar. Okay, so this is X bar. What's probably their average credit card debt is more than 2850? Okay, the notation is probability X bar greater than 2850. They're talking about X bar, so I put an X bar and then more than this. Once again, X bar has a normal distribution. That's what it says right here. X bar has a normal distribution. So what do you do to find this probability? You do a Z transformation. So Z transformation. Again, watch how I'm going to write the Z transformation out. So it's going to be probability X bar minus mu X bar over sigma X bar greater than 2850 minus mu of X bar over sigma X bar. Now this part turns into Z. And for this part, we're going to plug in the numbers 2850. Again, it says mu X bar and sigma of X bar. So I'm going to go back. This is mu of X bar. This is sigma of X bar. Those are the numbers that are going to go in there. So again, don't use this for sigma. Use this for sigma because it's an X bar question. So 2982, 52.5. 2982, 52.5. And now we'll calculate that number. And now you have to round. So that's why I don't want you to round until you have to. You have to round the number inside the parentheses to two numbers after the decimal. And the number is negative 2.51. Okay, now when it's a greater than, you do 1 minus probability less than the number. And the less than you look up in the table, less than negative 2.51, we'll go to the table. Negative 2.51, negative 2.5 is right here. The last digit 1 comes from here, and then you go to the right like that, and you go down that much. And you get 0.0060. And when you subtract, you get 0.994 or 0.9940. Okay, then I'm going to go ahead and go to part C. Again, it says 36 Americans randomly selected was probably their average credit card debt is between 2,900 and 3,000. The notation is probability. All right, I want someone to tell me the notation. What is it?
2,900 less than x, less than 3,000.
You are incorrect.
X bar.
X bar.
Very important, okay? I want to make sure you're clear. This is an X bar question. Okay, if you don't put the X bar there, I'm going to wonder if you understand that it's an X bar question. So everybody with me here?
Yes.
Yes.
Okay, once again, the previous slide, we said X bar is normal. So again, Z transformation. So, okay, so that's how you answer questions like this. You don't draw the bag. The bag is ridiculous. You wouldn't draw it. You just do Z transformation. The way it goes, 2,900 minus mu X bar, because it's an X bar problem, sigma X bar down here. I want you to notice none of these questions asked about X. It was only about X bar because we didn't know the distribution for X. Everything is about X bar. All right, the middle term, that mess is Z. For the other parts, I'm going to plug in mu of X bar. Mu of X bar was 2,982. Sigma of X bar, again, don't get that messed up. You have to use this, don't use this. If people use the 315, they just blindly take the number out of the question, it's going to be wrong because the sigma for X bar, you have to divide by square root of n. So this is the sigma of X bar, 52.5. So 52.5 here. And this other one, 3,000 minus 2,982 over 52.5. This is negative 1.56. This is 2,982 minus 2,982 divided by 52.5. And this is 0.34. Okay, and that's how you do it. And now you have to do a Z problem. And again, the way you do a Z problem when it's between, you do probably Z less than the number on the right, minus probably Z less than the number on the left. And now you look them up. 0.34. Okay, 0.34 is positive. So you look for 0.3 on the left, last digit from the top. 0.6331 for that one. The other one, negative 1.56, use the negative side of the Z table for that. Negative 1.5 you'll get from the left column, last digit from the top. You know, like that. 0.0594. Oops. .5737. That's how that one goes. Any questions on example 3, at least the part that I did? Okay, so again, I did skip a lot, but do those on your own because we need to go to the next section. I need at least a few minutes for the next section. But make sure you do them all on your own. And again, you read the problem carefully. Make sure you can tell if it's an X problem or an X bar problem. For X bar problem, it has to say you're going to take a sample, calculate an average, which is probably this happens. Then it's an X bar problem. And how do you do an X bar problem? Again, if the sizes of everything are small, you're going to have to make the X bar bag like you did way at the beginning. If things are bigger, there's still an X bar bag. It's just so ridiculously big that we're not going to make it. I still want you to understand how to make it if you had to. And then you're just going to remember it has a normal distribution. Central limit theorem says, don't worry, it has a normal distribution. So you could just do a Z transformation to answer the question, and the story's over there. Okay, any questions on section 8.1? Okay, let's go to section 8.2 then. We're talking about p hat now. So we're talking about the random variable x bar the whole day today. Now we're talking about p hat. The good news about p hat is it's almost the same thing as an x bar. So it's almost the same thing. All right, let me make sure you understand the story first. Remember, x bar stands for sample average. P hat stands for sample percentage. So the problem has to say you're going to take a sample and you're going to calculate a percentage. Instead of calculating an average, you're going to calculate a percentage. The way the story goes, the original bag will have zeros and ones in it. The original bag in the last section had a bunch of numbers. This time, the original bag will have zeros and ones in it, or you can think of it as yeses and nos. Every time it's a percentage problem, the population data is filled with yeses and nos. So like if I want to know the percentage of all Rio Hondo students that are married, if I ask every single person, I'm going to get a bunch of yeses and nos. If you put all those things in a bag, that's the bag we're starting out with, a bag filled with yeses and nos. Think of it as population data. And I'm never really going to ask you about drawing once out of the bag, but again, X, the original bag, we're going to call it X, and X is the answer you get when you draw one time out of the original bag. The percentage of yeses in the entire bag is called P. We said that first day of class, which normally is unknown. Normally you're trying to guess P, but in this section it's going to be given to you. So they're going to tell you the percentage of yeses in the entire bag. All right. What else? And we're going to form a new bag by doing what? We're going to take a sample. We're going to take some answers out of the original bag and calculate a percentage instead of calculating that. We're doing the same thing as section 8.1. The only difference is we're finding a percentage at the end instead of an average. We're going to form a new bag as follows. We're going to take a sample of zeros and ones of size n from the original bag. So we're going to take a sample. We're going to take some numbers out of the original bag. We're going to calculate the percentage of ones in our sample. Since it's in our sample, we call that p hat. We're going to put that in a new bag. We'll do this for all possible samples you can draw from the original bag. And again, this says the new bag doesn't contain zeros and ones. It has percentages in it. So old bag has zeros and ones or yeses and nos. The new bag has a bunch of percentages in it, a bunch of sample percentages. And again, they're going to word the problem one way, and when you think about calculating the probability, you can think about it a different way. So when they word the problem, they're going to say, you can take a sample, calculate a percentage. What's the probability you get this answer? Okay, so they're going to say you're going to take a sample from the original bag and calculate some kind of percentage. But when you're thinking about calculating the answer, you're going to pretend you made this new bag. The new bag is called p hat. And you're going to imagine we're drawing one time out of the new bag, the p hat bag. Here's a picture. Original bag, zeros and ones. Those are all the answers. If I was to ask every Rio Hondo student if they're married, for example, 1 means yes, they're married, 0 means no, they're not. That's original bag. But again, it's usually an imaginary bag of population data because we don't actually collect that data. Okay, so again, original bag has zeros and ones in it, or yeses and nos, and the percentage of ones in the entire bag, or like the percentage of all Rio Hondo students that are married. Normally, we would try to guess that, we wouldn't know it, but today it's going to be known. Okay, so they're going to give us that P, and then what we're going to do, and again, the original bag is called X. If you're going to draw one time out of the bag, the answer you get is X. But we're going to form a new bag by doing what? We're going to take some answers out of here. We're going to take a sample and we're going to calculate p hat, the percentage of ones in our sample. So like, for example, if I just draw these 5, so my n would be 5 if I took 5 out, and my p hat would be, this p hat would be 3 out of 5. 3 ones out of 5 total, which is 60%. Okay, then you take another sample, calculate another percentage, then take another sample, calculate another percentage, and you're going to put it in the bag on the right. The bag on the right is going to be called the p hat bag. So 60% will be there, and there'll be other percentages. Each number in the bag on the right is an answer after you take a sample and calculate a percentage of yeses or percentage of ones in your sample. So you put your answer in the bag on the right. Again, your bag on the right is called p hat. And you got to do this for all possible samples you can draw out of here. Again, take a look. The original bag, ones and zeros or yeses and nos. A new bag has all percentages in it. So the 72% means We took some numbers out of here, some answers out of here, and the percentage of yeses in that sample, 72%. Took a different sample, percentage of yeses in that sample, 38%, and so on. And you do this for every possible sample you can draw from the original bag, and you fill up this bag. The new bag has all sample percentages in it, not zeros. It doesn't have zeros and ones like this one does. It's all sample percentages over here. And again, when they ask you a question, they're going to say, if you take a sample out of here and calculate a percentage, what's the probability something happens? So sample, calculate a percentage, what's probably something happens? But that's equivalent, or you're going to think about it as, if we draw once out of here, what's the probability something happens? Okay, we did this already. We're not going to go through this. Okay, this part is important though. P hat is kind of like an X bar. Okay, P hat is, okay, let me do this real quick. I'm going to ask you guys a question and a yes or no question. How about wears eyeglasses? And if you wear eyeglasses, yes or no? Okay, yes, yes, no, yo, yes, no, no, yes, yes. Okay, so looks like 6 people are answering. So let's just pretend there's 6 students in here. So 6 students total, 4 said yes, you wear eyeglasses. So that's P hat. That's the percentage of you. Imagine I want to know the percentage of all Rio Hondo students that wear eyeglasses. That's P. But I'm figuring out the percentage of you guys who wear eyeglasses. That's P hat. It's a sample. 4 out of 6 of you said yes, I wear eyeglasses. Okay, so you can calculate this if you're dying to know. It's 66.7% or whatever it is. But now here's what I'm going to do. I'm going to ask you guys another question. Actually, I'm going to ask you the same question. Do you wear eyeglasses or not? Actually, you don't even have to type the answer, but I'm going to ask you if you wear eyeglasses or not. But I want you to pretend, instead of saying yes or no, if your answer is yes, you're going to say 1. And if your answer is no, you're going to say 0. And I'm going to take your answers. I'm going to find the average of your answers. So yes is 1, no is 0. I'll find the average of your answers. So the first person said yes. Second person said yes. Third person said no. Fourth person said no. Fifth person said yes. Sixth person said yes. And I'm going to find the average of these. How do you find the average? You add them all up and divide by how many you have. We have 6. And when you calculate it, look what you get. You get 4 out of 6. Should make sense. When you're finding the percentage, you're counting the yeses. Well, this is like counting the yeses. 1 for yes, 0 for no. If you add them up, it's like you're counting the yeses. We got the same answer. If you treat a yes as a 1 and a 0 as a no, then P hat and X bar are the same thing. They're basically the same thing. Why is that great? We spent so much time on X bar. We learned that X bar has a normal distribution. Same thing with P hat. Again, there's a small bag situation which I'm not going to go over. I'm not going to ask you that on the quiz anyway. You may see it in online homework. But when things are big, what's the conclusion? P hat has a normal distribution. That's it. Just like X bar has a normal distribution, P hat has a normal distribution as well. That's the story there. So, but instead of the condition n greater than or equal to 30, we have a different condition, npq greater than or equal to 10. You saw that one in section 7.4. It's showing up again. npq greater than or equal to 10. All right. So here is the central limit theorem for p hat. Now, when I ask you to state the central limit theorem on quizzes and exams, I'm always going to have you state it for X bar. So you're not going to ever have to state the one for p hat, but here it is. As long as the following conditions are true, this one, which you never have to state anyway, and then this one, npq greater than 10, which you will have to check, and I'll show you in a minute when we do a problem. You need npq to be greater than 10. As long as those things are true, then p hat has a normal distribution. That's the conclusion. P hat has a normal distribution. Since it has a normal distribution, in order to answer questions involving p hat, I'm going to do z transformation. That means I need to know what mu of p hat is and what sigma of p hat is. And I'm just going to give you the formulas. Here they are. Mu of p hat is equal to p, and sigma of p hat is equal to square root of pq over n. Okay. So again, what have I said? I haven't said much. I just said p hat is like an X bar, has normal distribution. And now we're going to do a problem. I'm going to definitely skip this one. Let's go to example 5. And all right. 56% of the students who enter America's colleges and universities graduate within 6 years. If 250 college freshmen are randomly selected, from American colleges and universities. Was it probably less than 64% of them will graduate within 6 years? This is example 5, part A. All right, first of all, let's read it again. 56% of the students who enter American colleges and universities graduate within 6 years. This is 56% of everybody who's ever gone to college. They'll graduate within 6 years. That's percentage for the entire bag, which is normally not known, but it's given in this problem. How do we know it's a sample percentage problem? They got to say, you're going to take a sample, calculate a percentage. Look, if 250 college freshmen are randomly selected, that's a sample. That's not all college freshmen, that's a sample, 250 college freshmen. What's the probability that this percent of them sample percentage? This is a p-hat problem. In other words, we're going to talk to 250 college freshmen. We're going to ask each of them if they're, well, it sounds kind of weird. How are we going to talk to college freshmen and ask them, are you going to graduate within 6 years? So I'm going to change the problem a little bit, okay? I'm going to say we talked to 250 college graduates, and we're going to ask them, did you graduate within 6 years? And we're going to calculate the percentage of them that graduate within 6 years. Well, so probably that percentage is less than 64%. So I want to make sure it's clear that in this problem you see sample percentage. Once you see sample percentage, you know it's a p-hat problem. Now, yeah, I think we're only going to get to do part A. But okay, you have to write down things at the beginning. Remember, there's still two variables going on here. There's x and there's p-hat. Instead of x and x bar, it's x and p-hat. X is always the original bag. X is the yes or no answer. What I'm thinking in my mind is if I draw once out of the original bag, well, I'm going to get a yes or a no, or 1 or 0. It's the yes or no answer when I talk to one person. When A means 1, a college graduate. I'm going to change it to graduate, okay? I just think it makes it a little bit easier to think about graduate. When a college graduate is asked if they graduated within 6 years. X is the answer when you talk to one person. And the distribution of X is unknown. That's a little bit of a lie, but I'm just going to write unknown. But they do give us P, and we can write down Q. P is 0.56, 56% graduate within 6 years. Q is 0.44, because these have to add to 1. So that's all the stuff you can write about X. Now, p-hat, what is that? This is the percentage in a group of 250 college graduates that graduated within 6 years. Now, to figure out the distribution, we have to check the condition first. The distribution is going to be normal. That's the whole point. But you got to check the condition first. This NPQ is a greater than 10. N is 250. P and Q are over here. You got to multiply all those together. I hope you get an answer bigger than 10. Let me see here. Okay, I'm getting 61.6. It's definitely greater than 10. So the conclusion is the distribution is normal by Central Limit Theorem because NPQ is greater than 10. Okay, then we need to write down the mu and the sigma for this variable. Mu of p-hat, the formula is that it's equal to p, so it's 0.56. And the formula for sigma of p-hat is square root of pq over n. So it's 0.56, 0.44, n was 250, square root of that, and that's pretty ugly, so I'm going to leave it like that. So you write all that stuff down at the beginning. Then we'll do the question. Part A says, what's the probability that less than 64% of them will graduate within 6 years? Again, the top part says 250 college graduates are selected. We're selecting a sample. What's probably that less than this percent of them will graduate within 6 years? Somebody help me with the notation for the question. The notation, very important. What is it? So since I'm asking you to find a probability, first thing you're going to write is probability. Now what goes inside there?
P hat
P hat, yes.
is less than 0.64.
Is less than 0.64. Wonderful. Okay, again, that shows me a lot. That shows me you saw it was a sample percentage problem, a P hat problem. Is everybody with me on the notation?
Yes.
Yes.
Okay. Now that I know that P hat has a normal distribution, how do you find this probability? You do Z transformation. Check out how it's going to be written. P hat minus mu of P hat over sigma of P hat. Same thing on this side. Because it's a P hat problem, you put mu and sigma of P hat there. Mu of P hat, sigma of P hat. The first parentheses, the part that has the variable in it, the P hat, that turns into Z. The other part, you plug in the numbers, 0.64 minus mu of P hat is over here, 0.56. And then on the bottom, this is sigma P hat, square root of 0.56, 0.44 over 250. All right. Now we got to calculate that number. Again, this might be a problem on the calculator. So 0.64 minus 0.56. Get the answer to the top. Divide. Now, we talked about earlier how to divide by a fraction. Now how do you divide by a root? Well, not divide by a root, but if you have a root and there's a lot of stuff inside the root, what I advise you to do, if this is only for people whose calculators do this, when you open a square root, if your calculator, after you open the root, if a parenthesis symbol shows up, then my advice to you is open more. That's really good advice. Now, if no parenthesis shows up, then forget it. But on my calculator anyway, when you open a root, one parenthesis symbol shows up, then open more. The reason I want you to open more is because whatever parenthesis symbol shows up, if you close it and you're not done with whatever is in the root, the rest of the stuff will not be in the root. So whatever parentheses opens up, you want to make sure not to close it until you've typed all this stuff inside the root. So my advice to you is just open a few more. That way, when you type in like 0.56 and you close the parentheses, for example, you didn't close this one. So I'm going to open on my calculator a few parentheses. I'm going to do 0.56 times 0.44, divide 250, get the answer. And then you can just push enter. You don't have to close them all. Just open them all, open a bunch. And then once you push enter, it'll close them automatically for you. 2.548, this is going to be 2.55. Sorry, okay, so 2.55. So if you got that, then you're in good shape. And now you just do the Z problem. And again, I know we're all good at that. When it's less than in particular, you just look it up in the table. So let's go look it up. 2.55. Is it positive 2.5 from here, the last digit from here? And you go like that. And the answer is 0.9946. Part C. What is the probability that between 48% and 55% of them will graduate within 6 years? Again, this is a p-hat problem. All of these questions are p-hat questions because, again, it says we're going to select a sample of this many people and calculate a percentage, which is probably that percentage is between here and here. Once you recognize it's a p-hat problem, the symbol p-hat is going to go inside the parentheses. And because it says between 48% and 55%, we're going to write 0.48 less than p-hat less than 0.55. Again, one of the big deals is that you recognize it's a p-hat question. You put the symbol p-hat in the parentheses. If you put an X, I'm gonna be like, I don't know if they get it. Okay, so you put the p hat there, and you tell me, hey, Greg, I see it's a p hat problem. Then we saw, let me go back a couple slides, that p hat has a normal distribution. Okay, so since it's normal, if you want to find that probability, you have to do a z transformation. So here we go. Z, that's all you do. All the problems are z transformation problems. So z transformation. Watch how I'm going to write this. It's going to be 0.48 minus mu of what? Mu of p hat, because it's the p hat problem, divided by sigma of p hat. Middle is p hat minus mu of p hat divided by sigma of p hat. And the right side is 0.55, again, minus mu of p hat over sigma of p hat. Now, the one with the p hat in it, this whole mess, that turns into z. So the middle term is z. The other terms, we're going to plug in numbers. We have 0.48 here. And now for mu of p hat, let's go find out what it was. So here, mu of p hat is 0.56. Sigma of p hat is this mess over here. Okay, let's go forward. 0.56. Okay, now this is going to be 0.56, 0.44 over 250 square root. Some room here. Okay. Other side, 0.55 minus 0.56 over, again, this square root here, 0.56, 0.44 over 250 square root. All right, now we got to calculate those numbers. All right, let's see. 0.48 minus 0.56, answer. Now divide, now open a root. When you open the root that's on the bottom there, on your calculator, after you open the root, if a parentheses symbol shows up, you got to be careful, because if you close this parentheses and you don't type all this stuff in the root, then it won't all be in the root. As soon as you close the parentheses, the root is done. So my advice again, when you open a root, if a parentheses symbol shows up, that's not going to happen on every calculator. Does it on mine though. If a parentheses symbol opens up, what I advise you to do is open some more. Don't be afraid. Push the open parentheses button. It's right above the number 8. Okay, just open a few. And then type 0.56 times 0.44 divided by 250. And if you close a couple of parentheses, it's okay. As long as you don't close this one, the first one, until you're completely done typing all this in, then you'll be fine. And the answer I'm getting is negative 2.5. Well, it's like 48, but round it, it's negative 2.55 for that one. Let me type the other one. 0.55 minus 0.56, answer, divide, square root. And again, after I open the square root, I'm opening more parentheses. Now 0.56 times 0.44 divided by 250. Answer, this is negative 0.32. So if you got those numbers, again, you're typing it in right. Now, what do you do when it's a between problem? When it's a z between problem? There's a formula you're supposed to use. Probability z less than the number on the right minus probability z less than number on the left. And now those are both less than, so you look them both up in the table. We'll look up this one first, negative 0.32. Negative 0.32. And again, you look up negative 0.3 here. The last digit 2 over here. I'm getting 0.3745 for that. Minus. Now we'll look up this one, z less than negative 2.55. Again, you can use the negative side of the z table because it's a negative number. This time we're looking up negative 2.55. Except for the last digit, you look up the rest on the left column right here, negative 2.55. Last digit up on the top row right there, and you go like this to the right and like this downward, and you get 0.0054 for that one. And that's pretty much it. You subtract those and that's it. So let's see, 375, no, 3745 minus 0.0054. Answer 0.3691. That's example 5.